In section 2, we're going to talk about describing sets of data. So here we're going to deal with this idea of descriptive statistics and talk about some of the basics. So the two common ways to describe a set of data is either graphically or numerically. So we'll start out with just some basic graphs. So this is our first graph. This is a graph that's based on the variable basically students' favorite after-school activity, and you can see from the x-axis of the graph that the different categories are things like earn money, play sports, school clubs, visit friends, watch TV. Of course, this type of graph, this is a basic bar graph, so these are very, very common. One of the most common graphs, and also in part because it's so common, one of the most misused graphs. Lots of times people will misuse graphs, and since the bar graph is so common, it's a common example of a graph that is misused very often. The type of data that's presented in the graph, that's one of the things you should always think about whenever you think about how to graph a variable. It's the first thing you should think about, or how you're going to analyze data in general, is what type or types of data do you have. So a bar graph is designed for qualitative data, and you can see here that this is a qualitative variable. Along the x-axis we have these outcomes for this variable, which are after-school activities, things like earn money, play sports. Of course, those are non-numerical outcomes, which means that this is a qualitative variable. One of the things to be careful about is thinking about how many variables there are on this graph. Do keep in mind that this is a single variable. There's one variable, which is after-school activity. There are 5 bars, meaning there are 5 categories for this variable. So there's one variable and 5 categories. So make sure you distinguish there between the variables and the categories of that variable. When you have a qualitative or categorical variable, then of course each of the bars represent the outcomes or the categories. They do not represent different variables. One of the things to always look at with a bar graph is bar graphs are fairly flexible, and sometimes the y-axis will be frequencies and sometimes it will be percentages. Most commonly it's frequencies, and that's what you will see here. You will see the y-axis of this graph representing frequency, the x-axis representing the variable itself. So basically the height of the bars tells you how common each choice was whenever we ask students their favorite after-school activity. What most people tend to notice when they look at a bar graph is they tend to notice the tallest bar. They do these studies sometimes where they'll show people a graph and they'll take the graph away and they'll say, what did you remember? And the most common thing to remember in a bar graph is the tallest bar, the most frequent category. And in general, that's what people tend to remember with graphs, is they tend to remember what's most common. Lots of times people will say they remember nothing, but when they do remember things, and we all kind of naturally do that, we look for the tallest bar, at least most of us. So those are the things that people tend to remember. They tend to remember what's the most frequent outcome for this variable. So let's dive a little bit deeper into why a bar graph is used for qualitative data. It's one of the mistakes that people will make with bar graphs is they'll put a quantitative variable in a bar graph. If you click buttons in Excel, you can make it put quantitative data in a bar graph, even though that's not what they're really designed for. But it comes down to the x-axis. The y-axis is just a frequency, but the x-axis here represents categories, and that's how a bar graph is designed. So these 3 questions kind of sum up the differences between how we graph a qualitative variable and a quantitative variable. Notice in this graph, the questions are, in the graph, is there any meaning to the width of the bars? And of course there's not. If you look at the first bar, the earn money bar, you look at the height, that tells you the frequency, but the width has absolutely no meaning. All we do is make all the bars the same width. If this was a quantitative variable, though, that x-axis would have to become a real number line, and then that would mean that the width of those bars would have meaning. And that's just not the case when you have a qualitative variable. With a bar graph, we assume it's qualitative, which means we just make all the bars the same width, which represents no quantity. It's just best visually to keep them all the same width. Is there meaning to the spacing between the bars? Same thing. We just evenly space them. We just make everything uniform. But there's no meaning to the spacing between those bars. And does the order matter? Well, of course the order doesn't matter. These are just categories. There is no really ordering. You can see the software put these categories in alphabetical order, but it really doesn't matter what order the bars are. If this is a quantitative variable, then order absolutely matters, because as we know, if you have a quantitative variable and this is a real number line, then of course those bars are going to be in numerical order. Those are some of the key differences between what we do whenever we have an axis that is a qualitative variable and an axis that is a quantitative variable. When we have a quantitative axis, that axis becomes a real number line. When we have a qualitative axis, we just keep everything uniform so that it's nice and easy to interpret based on what you see visually. So now let's talk about some quantitative graphs. There are two quantitative graphs that we focus on, which is the idea of a stem and leaf plot and then the idea of a histogram. And these two graphs are similar, but they each kind of have their own purpose, and there's some distinction between the two. We'll start with the idea of a stem and leaf. So the variable set that we're going to use is this. This is 1 year infant mortality for countries in Western Africa, and you can see the data there. So when you create a stem and leaf is essentially a plot that uses the data points themselves. And we divide the data points up into leading digits and trailing digits. We call the leading digits the stem, the trailing digits the leaves, and of course that's where we get the name stem and leaf plot. So for example, in this data set, that first data point is 84. So for our purposes, we will always just make the ones place the leaf. So since that data value is 84, that would mean 4 would be the leaf, which means the 8 is the stem, and we're going to break it up in that way whenever we create the graph. The next data point is 147, which means the leaf is 7 and the stem is 14. So when you draw this graph, what you do is you start by basically listing your stems. You list your stems vertically. The stems in this case range from what? The lowest value I see is 51. The highest value I see is 151. So that means your stems are going to range from 5 to 15. So you just list all the numbers from 5 to 15. Then you use a vertical line in order to separate the leaves. And then you go through each data point and you write the leaves with the corresponding stem. So if you do that in this case, you're going to get a plot that looks like this. This is a basic stem and leaf plot for this data set. You can see to the left of the line, those are all your stems. Your stems range from that lowest data value of 51 to that highest value of 151. So your stems range from 5 to 15. Then to the right, you simply identify the corresponding leaf. So there's only one value of 51, so you put that 1 over there. You have a value of 84, a value of 86, and a value of 88, and you just list those leaves horizontally, and you do list those in order. You don't put any commas or anything in the stem and leaf. Everyone who looks at a stem and leaf knows that those are separate values that represent the outcomes from this data set. When we look at these quantitative graphs, there are two main purposes of them for both the stem and leaf and the histogram. And that is really to look at and see whether or not there's any extreme values in your data set, and to also look and see what the shape of the data is. So with the stem and leaf, you're basically looking at the shape created by those numbers whenever we talk about shape. We're going to talk about extremes now, and we'll come back to the idea of shape once we talk about both graphs. But the shape in a stem and leaf is just looking at the shape created by those numbers. Extreme values are the other thing that we look at, and extreme values are basically a data point, or it could be more than one data point, that's essentially separated from the rest of the data. It's an unusual data point that's separated from the rest of the data. These are very important when we go to calculate statistics, both shape and extreme values, because they can have a drastic effect on things that we calculate. If you think about something simple like income is one of those cases where you got to be really careful in terms of if you want to look at something like average income. If you look at the average income and you calculate just a regular average, then what can happen if you have extreme value is you can really make the income look like something that's not representative of the population. Like if everyone in the class identified their income and we averaged them all, maybe it would be a good measure of what the average person made in the class, but maybe it wouldn't. But if you took someone like LeBron James and you put his income in with everyone else's, then what would happen is the average income would end up probably being higher than everyone in the class except his, because his would be so extreme. It would be separated from the rest of the data. So that's the kind of impact that an extreme value can have. It can really influence the outcome and make something like an average not even very meaningful because it's not representative of the group because of one extreme value. The shape also has that same kind of impact. When you have skewness in your data, it can really pull the mean or it can pull that typical measure of average toward those tails or towards those extremes in the tail, which will give you skewness in your data. So in this case, are there any extreme values in the data set? And there is one. Notice that the 51 is by itself. We have no values in the 60s, no values in the 70s. It is important to still include those categories in your graph. That's one of the things you'll notice. It's one of the things that make it easy to see that 51 is extreme. 51 is extreme because it's separated, and it's easy to see that it's separated because there's no values in the 60s and no values in the 70s. So that's the idea of a stem and leaf. So we're going to look at this same data set, but we're going to look at it in the form of a histogram. So this is a histogram of that same data. A histogram looks very similar to a bar graph, but there's one big difference between a histogram and a bar graph, and of course that is the x-axis. The y-axis here still represents your frequency, but notice the x-axis here represents the infant mortality in Western Africa, which is numerical, so now that x-axis does become a real number line. So the width, things like the width of those bars now has meaning. So does the spacing. There is no spacing because there's no numerical spacing between the categories. This is based on a picture of a frequency distribution, as you should have read in the notes. And of course, all those things that we talked about earlier, the width of the bars, the spacing, the order, all those things now matter because this is a numerical quantity. If you compare this to the stem and leaf, I like to talk about how they're similar and how they're different and when you should use each one. These are very similar graphs. A histogram and a stem and leaf are very similar. And you should have seen this in the notes, but if you actually turn this graph sideways and you look at the shape of the bars, what you will find is, since I set these up the same way and it's the same data, you will find that the shape created by these bars is exactly the same as the shape created by the numerical values. So that's what is very similar, is identifying shape is the exact same in both a stem and leaf and a histogram. One is basically just turned sideways. In terms of extreme values, you will notice, if you look at this histogram, you will notice that there's one bar that's out here by itself. Now, the difference between a stem and leaf and histogram, of course, is in the stem and leaf, we know that this value is 51. Through the grouping process in a histogram, it's one of the downsides of a histogram. Through the grouping process, we lose the ability to recover the original data. So when you see that bar with a frequency of 1, the bar clear to the left, if you look at the height of it, you can see the height is 1, which tells us there's one data point there. If we look at that one data point, we can tell it's between 50 and 60, but we don't know exactly what the data point is. And that's what you lose when you move from a stem and leaf to a histogram. Is in a stem and leaf, you can actually recover your original data. In a histogram, you cannot. So that's the big benefit of a stem and leaf. Now, at the end of the day, most of the time when we deal with quantitative data, most of the time we do a histogram, because you can notice with the stem and leaf, if you have a really big data set, for example, it's going to become a mess whenever you create a stem and leaf for that data set. Also, if you don't have data points that fit nice and neat into that leading digits and trailing digits idea, then you're also going to have an issue with setting it up nicely. So at the end of the day, a histogram is the most common quantitative graph, But in a case like this, a stem and leaf would actually be preferable. But in most cases, most data sets, honestly, because we typically deal with way bigger data sets than what you would want in a stem and leaf. So because of that, we usually use histograms. The last thing I've already mentioned, but we need to talk about, is the different shapes. So there's a lot of different shapes that you can identify in a histogram and stem and leaf. With a histogram, you just look at the shape of the bars. With a stem and leaf, you look at the shape of the numbers, but it works the same way. Hopefully you've seen that those are the same when you create them for the same data set if you set them up the same. We'll focus on 5 different classifications of shape, and that's what I have next, is just a quick run through of what those shapes are. This is the first one. The first one is when you have that increasing, decreasing pattern. The left side is a mirror image of the right side. That is your typical symmetric shape. When you say symmetric, all that's really guaranteed is that the left side is a mirror image of the right side. But I will tell you that in statistics, most of the time when we say symmetric, it typically has that increasing and then decreasing shape. Because whenever we have other kinds of shapes, we typically identify those with other terms besides symmetric that indicate that they have additional characteristics beyond just being symmetric. An example of that is this next one. If you look at this one is actually what we call uniform. You'll notice that a uniform is also symmetric, right? This uniform graph is symmetric. The left side is a mirror image of the right side. But in addition to being symmetric, all the bars are exactly the same height, or all the classes have equal frequency. And since it has that additional characteristic, we would not say this is symmetric. We would say it's uniform. And whenever we say it's uniform, we know that all uniform distributions are also symmetric. But whenever we say uniform, we know that in addition to just being symmetric, all of the bars are the same height. So that is a uniform distribution. These next two kind of go together. These are the skewed distributions. What I recommend you always do when you look at graphs is just kind of start at the highest points. That's a good place to start. So like as you notice in the symmetric distribution, the highest bars had the left side and the right side of those bars was a mirror image of each other. In a uniform, when you look at the tallest bars, well, they're all equal. So you know it's uniform. In this case, you'll notice that the tallest bar is to the left, and we say that this has a tail to the right. So we say from that tallest bar, it tails to the right, and it tails to the left. So that's the terminology that we use. The tail to the right, you'll notice, if you look at that tallest bar, the tail to the right is longer than the tail to the left. So that tells us that this is a right skewed distribution, or it is skewed right. So that's the way you tell the difference between skewed right and skewed left. Skewed is the opposite of symmetric. So never say that a graph is both symmetric and skewed. If it is not skewed, then it must be symmetric. And if it is not symmetric, it must be skewed. It cannot be both. Those are opposites of each other. A skewed distribution means it's not symmetric first and foremost. And then you need to determine the direction of the skewness, and the direction is always the direction of the longer tail. So here's one that's basically the opposite. If you look at the highest frequency class, you'll see that it has a longer tail to the left than it does to the right. So that is what a skewed left distribution looks like. Here's the last one that will be responsible for identifying. And when you look at the tallest frequency class here, you'll notice that the two tallest bars are actually not together. And that's the first thing you should notice. Now, this one could be symmetric, but it's not. But if the two tallest bars are the same height and everything else is symmetric, but it still has these two tallest bars, we still have to notice that these two tallest bars are not together. That's an important characteristic. Anytime you have the two highest frequency class, or basically you have two humps, it doesn't even necessarily have to be the two tallest bars. If you have two humps in a distribution, that's what we call a bimodal distribution. What a bimodal distribution typically means is it typically means you have more than one group in your data, and these groups, usually it'd be two groups if it's bimodal. You have these two groups in your data that's measuring differently. So what can happen, for example, is if you put all adults in the United States together and you create a histogram, you'll get a bimodal distribution. It's because, on average, males and females are different height. So what will happen is basically one of the high bars will represent average female height, and the other high bar will represent average male height. And when you put those two groups together in the same histogram, those high bars don't match up because on average males are taller than females. So when they don't match up, you end up with this bimodal shape where one hump basically represents the peak for one group and the other hump basically represents the peak for the other group. So what you should do in a case like this where you get bimodal data is you should actually separate the groups. And that's why if you go to the doctor, they don't compare all adults whenever they look at heights. They typically look at, they compare you with other males or other females. So those are the graphs, and those are the common graphs that we use. There's lots and lots of different graphs, as you probably know, but those are the common ones that we use and the ones I like to talk about. We really use a histogram more than anything, but it is important to understand the difference between the qualitative and quantitative variables, so I like to go through that idea of a bar graph so you can see that distinction. Also, it's nice to see a stem and leaf because those are useful. Sometimes if you have a small data set, it's nice to just quickly jot down a stem and leaf because it's much more difficult to draw a histogram by hand. Of course, these graphs are usually done with software. I don't make you draw a bar graph or a histogram by hand. I will have you create a stem and leaf, but I won't have you create a bar graph or a histogram by hand. I'll give you a picture and you need to be able to interpret the graph based on the picture. Okay, the other way that we describe data is numerically. So before we get to that, we need to just make sure we're on the same page as far as some notation. Some of you may have seen summation notation before, and some of you may not have seen this before. But we use summation notation a lot in the field of statistics, so it is important to make sure you understand how to deal with this mathematically. So in a data set, we will have, when we have a single variable in statistics, we call that variable x. So basically the first data point is x1, the second data point is x2, and however many data points we have, our sample size, we call our sample size n. So you have x1, x2, x3, all the way until you get to x sub n. So we do lots of different mathematical operations on that set, and we typically sum over the sample size in statistics. So we don't always write the indexes if you've dealt with sums before. We don't really need the indexes because we're basically always summing from 1 to n because we're summing over the data or the sample that we have. So therefore, we use this shortcut notation in order to write sums. Instead of writing x1 plus x2 all the way to x sub n, we just simply use this capital sigma sign and we just say the sum of the x's, and that just means sum your x values or sum your data values. And that is very common notation. So let's just look at a very simple example so you can, so we make sure that we're on the same page as far as how we denote things. So just suppose we have just a small data set and we have 4 data points. We have the data points 4, 2, 5, and 1. So first, if you want to denote the data, this is how you would do it. So your first data point is x1, your second data point is x2, your third data point is x3, and your last data point is x4. And of course our sample size here is 4 because we have 4 data points. So you go from x1 to x sub n, n in this case being 4. 4 is our sample size. That's the way we would denote that. If we want to write that out as a sum, we will just simply write the sum of x. And what the sum of x means in this case is the sum of x means I want to sum these x values or these data points. So it just simply means take x1 plus x2 plus x3 plus x4. And if you sum those values, that just means 4 plus 2 plus 5 plus 1, which gives us a sum of 12. So that is your typical summation notation. And like I said, we use this a ton in this class. The next thing we need to talk about with summation notation is properties. There are 3 main properties that we deal with. We will manipulate sums algebraically in here to some extent, and these are the 3 properties that are really important to make sure you have a grasp of as we go into this material of describing data. So here is the first one. So in these sums, of course, x is your variable, the capital sigma is the sum, and c just represents some constant. So it's just some constant value. It could be 4, whatever. But we're just going to call it c. So the first property is basically if you are summing a constant times x, and you have a constant within that sum, then what you can do is you can always pull the constant out in front of the sum. You can always pull a constant out in front of a sum. So this might look a little different than what you're used to, but it's really very similar to what you've done before in algebra. Whenever you have a constant within a sum, you can always pull it out as long as it's in all the terms. And what this is saying is there's a constant in every term. So it's just like this. It's just like if you have CA plus CB. Well, you can pull a C out in front because that is a constant in both of those terms. And it looks a little different, but it's exactly the same concept as what you've done before in algebra class. The second property is this. What happens if I just sum a constant? So what happens if I sum a constant like I sum the constant 5 and I sum it 3 times? Well, if you sum a constant 5 3 times, then you basically get 5 plus 5 plus 5, which is 15. That's the way it works. Well, by our definition of multiplication, we know what multiplication is. Multiplication is nothing more than repeated addition. So if I simply take 5 plus 5 plus 5, that's the same as 3 times 5, which is 15. So the way it works in these sums is if you take the sum of a constant and you're summing it n times, because remember, we're summing over the sample size, which is n, the sum of that constant is nothing more than just n times the constant. It's like if I sum 5 3 times, then n is 3, the constant is 5, and I get 3 times 5, which is 15. Just remember that multiplication is repeated addition. That's really where this comes from. It just comes from that definition of multiplication. The last one is this. This is our third property. And these are the ones that we use. What if we take the sum of x plus c? So we have these basically 2 different terms, and you can have more than 2 terms. This applies if you have a trinomial there as well, not just a binomial. But basically what you can do is you can sum each part. So we can rewrite the sum of the quantity x plus c into 2 parts, and we can just simply take the sum of x plus the sum of c. This actually works because addition is commutative. The commutative property of addition basically says a plus b equals b plus a. It doesn't matter what order you add in. So it doesn't matter if you first add x plus c and then you take the sum, or it doesn't matter if you sum each part, sum x and sum c, and then add those together. It doesn't matter what order you add in because addition is commutative. So since it doesn't matter, the sum of the quantity x plus c is the same as the sum of x plus the sum of c. Of course, we can further simplify this one because we, just in the previous property, we said the sum of c is equal to n times c. So you can actually rewrite that sum of c as n times c, and we can actually simplify this further to the sum of x plus n times c. But these are properties that are important to know. You're going to use those algebraically in this section, but we will continue to use these properties as we solve for sums throughout the remainder of the semester. So let's do some examples. Make sure we understand how these sums work. So we're going to go back and use that same data set where we just had 4 data points. That means n equals 4. We have 4 data points, which are 4, 2, 5, and 1. So let's just talk about how we sum some different expressions. So we're going to start with just the sum of 7x. So there's 2 ways to do this, and I'm going to show you both. The first way is just to create a table. So let me just show you the table and then I'll talk you through it. So the first column of this table is simply just my x values, which are 4, 2, 5, and 1. Those sum to be 12. So the numbers at the bottom, of course, are the sum. One way to do this is I need the sum of 7x. So what happens if I create a column of 7x values? Well, 7x just means I take 7 times each x value. So if I take 7 times 4, I get 28. 7 times 2, I get 14. 7 times 5, I get 35. And 7 times 1, I get 7. So that's a list of my 7x values. If I sum those, I get 84. So that is the sum of 7x. The sum of 7x is 84. That's one way to do this problem. With sums, it is very nice to get in the habit and get used to creating columns for what you need in order to calculate sums. That's one important idea here. Don't always just do it that way. However, you also need to make sure you understand the algebra in order to be able to get to that value of 84. Because there will be times when we do algebraic manipulations on sums and you don't have any data. So you have to be able to manipulate the sums algebraically because you can't just use the columns. So sometimes the columns are useful and sometimes they're not. So when you do these kind of problems in the homework, do make sure that you understand the algebraic steps to get to your solution. I would actually recommend you do it both ways and make sure you get the same answer both ways. So algebraically, we have to use our properties. We have a constant within that sum. So we can first pull out the constant, and we can rewrite this as 7 times the sum of x. Well, we already know the sum of x is 12. That's the sum of that first column there in the table. So we can rewrite that as 7 times the sum of x, or the 7 times 12. If you take 7 times 12, you get 84. That is the way we simplify that algebraically. Of course, we do need the sum of x. And that is very common. It's very common that when you calculate statistics, you will need the sum of x. It's actually also very common that you need the sum of x squared. Those are two common quantities that you need when you calculate certain statistics. Let's do another one. Suppose I want to take the sum of x minus 5. So we'll start by creating a table, same thing. You create a column that is your x values, but we also need a column that is my x minus 5 values. So all you have to do to get the x minus 5 column is you just take each x value, you subtract 5. So you take 4 minus 5, you get negative 1. 2 minus 5, you get negative 3, and so on. That gives you your list of x minus 5 values. Now we know that sum of x minus 5 is negative 8. The other way to do this is algebraically. So the first thing we would need to do here is break this up, right? So we have the sum of x minus 5 quantity, but we can rewrite that by breaking this sum up and rewrite this as sum of x minus the sum of 5. We know the sum of x is 12, so we can just simply replace sum of x by 12. Whenever we sum a constant, this is our other property, we sum a constant of 5, we take n times that constant. So n is my sample size, which is 4, so that's where that 4 comes from. That 4 is your sample size. 5 is the constant. If you take 4 times 5, then you get basically n times c. That will give you 20. We end up with 12 minus 20. That gives us a sum of negative 8, which is, of course, the same thing as what we got from the table. These two things will always match up, and if they don't, then you made a mistake somewhere. Here's another one. With the table, we still have that list of our x's. Now we have a list of 3x plus 8 values. So you just plug in 4 for x. So you plug in 4 for x, you get 3 times 4, which is 12, plus 8, that gives us 20. When x is 2, you plug in 2 and you get 14, and so on. So that's a list of 3x plus 8 values. If you add those up, you get 68. If we do this algebraically, our first step is to break this up and to rewrite this as the sum of 3x minus the sum of 8. Then we can deal with constants. We can pull that constant out in front of that sum, and we can rewrite that first term as 3 times sum of x. That second term is just the sum of a constant. So again, our sample size is 4, so that's n times c, n being 4, c being 8. We can then rewrite the sum of x as 12. We know the sum of x is 12, so that's 3 times 12. 4 times 8 is 32. 3 times 12 is 36, plus 32. That gives us that same quantity of 68. Last one of these. So it's very common in statistics that you will end up squaring things. And we'll talk more about this in the next section when we actually calculate a statistic where we do have to square it. But it's very common when you calculate statistics that you will end up with squared quantities. So this is an example of that. So in order to create the table, it's really nothing different. You just have a list of your x values, and then you have a list of 2x minus 1 quantity squared values. So if you plug in 4 in here for x, you get 2 times 4, which is 8, minus 1 is 7. You square 7, you get 49. So you get, when x equals 4, 2x minus 1 quantity squared is 49. When x equals 2, 2x minus 1 quantity squared is 9, and so on. You just plug each of those x values in. That'll give you your 2x minus 1 quantity squared values. Sum those, you get 140. So that's whenever you do this with the table. So when you do it algebraically, it's a little bit different because we're going to need the sum of the x's. But the big difference here is, since this is a squared quantity, when we simplify this, we're also going to end up with an x squared value in there. So this is very common. So I just added to this table, I just added a list of x squared values in there. So all you do to get the x squareds, of course, is you just square your x values. So you take 4 squared, you get 16, 2 squared is 4, 5 squared is 25, 1 squared is 1. You sum those, and you get 46. So to do this algebraically, you're actually going to need both the sum of x, which is 12. You're also going to need the sum of x squared, which is 46. So to simplify this algebraically, well, we can't really do anything with the sum until we deal with that squared. So the first thing you have to do is you have to square that thing out. So you have to use FOIL, basically. So you square that thing out, you get, when you square 2x, you get 4x squared. You take 2x times negative 1, you get minus 2x, but there's 2 of those, so that's minus 4x. And then you get negative 1 times negative 1, which is plus 1. So all I did there was square that out. You can use FOIL, and you'll see that that's what you get. Once you do that, then you can start using your properties. Now we can start breaking this up, and we can start by summing each part. So we can break this up into 3 different sums. The sum of 4x squared minus the sum of 4x plus the sum of 1. And this is always kind of the process that you go through with these sums. You always simplify anything you need to simplify first. So in this case, we had to square it. Then you break things up. You break it into the parts. You sum each part. The next step is to now look at each part and use those other 2 properties where we either pull the constant out front or we deal with the sum of a constant. So that first term, where we have the sum of 4x squared, we can pull that constant 4 out front, and we're left with 4 times the sum of the x squared. The second term, we can also pull 4 out, and we're left with 4 times sum of x. And then in that last term, we're dealing with just the sum of a constant, the sum of 1. So we, again, n in this case is 4. There's 4 data points. So it's n times that constant, so that's 4 times 1. Now we plug in. We know the sum of x squared is 46. That's given to us in the table to the right. So we take 4 times the sum of the x squareds. The sum of the x squareds is 46, so we just plug that in. Then we get minus 4 times the sum of x. The sum of x is 12, so again we plug that in and we get 4 times 12. And then we get plus 4 times 1, or just 4. If you work out the math there, you'll get 184 minus 48 plus 4, which gives you 140, which is what we should expect. It's the same thing as we got whenever we did this using the table. So that's the idea of sums. And those sums, like I said, are very important. Lots of things that we do in statistics deal with sums. It's very common that our formulas will have this summation notation included in it. The last thing we're going to do in this section is we're just going to briefly talk about just some of the basic statistics, and then we'll do more of these in the next section. So here's our example. We're going to talk about basically the measures of center. That's the only thing we're going to talk about here is the measures of center or central tendency. So everyone's probably heard of the mean, median, and mode. Those are your typical measures of center. So here's our example. Suppose that we take a random sample of 8 fuel-efficient cars and record the gas mileage. Calculate the following for the results. So these are our data points. Our data points are 31, 40, or 33, 41, 45, 35, 37, 39, 37, 34. Okay, so we're going to start with the mean. So when most people talk about an average, they're talking about a mean. A mean is just a simple average. The sample mean is calculated by summing your data points and then dividing by how many you have. So we're all familiar with the idea of an average. So the first thing is you list out your x values and you take the sum. The sum of the x values here is 301. I put the x values in order here. You don't have to do that to calculate the mean, but when you calculate the median, you need to put the data points in order. So I like to just kind of do it all in one step. So it's kind of nice if you just list your x values out in order, and then you take the sum of them. That gives you that 301. To calculate the mean, we just take that 301 divided by 8 because there's 8 data points. N is 8. N is always your sample size, and that will give us our sample mean of 37.625. Do notice the notation. The mean is denoted by, I usually call that X bar. It's basically X with that line over top of it. That is the way that we denote the sample mean. And that is for the sample mean, not the population mean. We denote the sample mean by X bar, is how we usually say that. The median. So the median, there's not really a formula. You have to put the data points in order and basically find the middle value. If there's an odd number of data points, then there is one value in the center. If there's an even number of data points like we have here, then you take the two middle ones and you basically take the mean of the two middle ones. So in this case, that's really simple because the two middle ones are the same. The two middle ones are both 37. So if you take 37 and 37 and you average it, of course, you just get 37. So the mean here is 36. The mean here is 37.625. The median is 37. Let me talk a little bit about the difference between these two and what you have to be careful of. Both of these are used for quantitative data. The big difference is the mean is sensitive to extreme scores and the median is not. So what I mean by that is just suppose that you take that last value there that is 45. And it's not realistic, but let's just suppose we change that last value of 45 to 450. If that last value was 450, notice that the median does not change at all. The median is still 37. However, if that last value is 450, then that's going to drastically change the mean because you're going to get a much higher sum. And the mean is going to be way higher. So the mean is sensitive to the fact that you have that extreme value out there, and the median is not. That is an important idea to keep in mind. So if you have a variable like income, like I mentioned before, where you're looking at average income, the mean is not a very good measure because if you have extreme values, if you have LeBron James in your data set and you average his income with everyone else's, the mean is going to be really high. The mean income in the United States is actually really, really high because of the top 1% or 0.1%. The mean is really high in the United States. If you ever hear them report income, what you'll notice is they don't report mean income. They actually report median income. And median income is a much better measure because it's not sensitive to those extreme scores. So the mean and median are both used for quantitative data. The mean is best when you do not have extreme values. The median is best when you do have extreme values. The third one is the mode, and the mode is not typically used for quantitative data. We typically use it for qualitative data because if you say something like the average student is female, then that just means there's more females than anything else. So it's good, and you can't perform mathematical operations when you don't have numbers, so you can't do a mean or a median. So the mode is nice when you have qualitative data, but the mode is just simply the most frequent score. In this case, it's simple. There's two 37s. Everything else just occurs once. So the mode here is 37. There are some big issues with the mode, which is why we don't like to use it, but we do use it for qualitative data because that's really the only option. But we don't really love to use the mode for quantitative data because it has issues like it doesn't always exist. What happens if all your data points are different? Then you have no mode. Or you can say that they're all the mode, but that doesn't make much sense. What happens if you have two 37s and two 45s? Then you have more than one mode. So the mode is a statistic that we don't love to use and we don't use for quantitative data, but it is a very good statistic for qualitative data because we can't perform any mathematical operations on those outcomes because they're non-numerical. I like to just mention the idea of the sample mid-range. I'm not going to spend too much time on this, but you should know how to calculate it. There are a bunch of different measures of center, so I like to give you one that's just not very good. The mean, median, and mode are all our common measures. We use the mean and median for quantitative data. We use the mode for qualitative data. The mid-range is another one, but it's not a very good one. There's lots of other measures that are not very good. I like to use this as an example of one that's not that great. The mid-range is just the low plus the high divided by 2. So in this case, you would take the 33, the lowest score, plus the highest score of 45, and just average them. The mid-range is one of those where it's totally based on any extreme values you have in your data because it's only based on the high and the low value. So you have all these data points and you're just using the lowest and the highest to figure out the average. That in itself doesn't make a lot of sense. Now, if you have a perfectly symmetric distribution, the mid-range, the mean, median, mode, they'll all be the same if you have perfect symmetry. So in some cases, the mid-range can be good. But the deal is when you start to deviate from a symmetric distribution, very few measures hold up and are good measures. The mid-range is an example of a measure of center that is just not a very good measure. It's only good whenever your data is perfectly symmetric, and that's the case with lots of different measures. Sometimes you'll see people use some of these, and I just like to mention it's something that you shouldn't do. Anytime you look at a statistic and it's only based on 2 values, and those values are the highest and lowest value in your data set, you know it's probably not very representative of your data as a whole, which means it's probably not a very good measure. The other thing that I want to mention with the mean and median is shape. Because if you're ever in doubt about the shape of a distribution, what you should do is you should actually compare your mean and median. And it's because of those characteristics we talked about. If your mean is bigger than your median, it actually tells you that your distribution is skewed to the right. Think about the picture of a right skewed distribution, and this isn't the best picture, but it's a right skewed distribution. The markings on there really don't mean anything, but this is a right skewed distribution. So what will happen is the median will divide the distribution in half. Exactly half your data will be below the median, and exactly half your data will be above the median. The mean, however, works differently. The mean is the numerical balancing point of the distribution. So you could actually do this. If you had this distribution, you could actually figure out what point would this in two-dimensional space perfectly balance. And the deal is that long tail to the right is going to make your mean move in that direction. And if you think about it from what we talked about earlier, this should make a lot of sense. If you have extreme values to your right, your mean is pulled toward those extreme values. And that's basically the way this works. The mean is always more affected by extreme values than the median. So the mean in a right skew distribution is going to be pulled more to the right than the median. So if you get a mean that's bigger, that means the mean must be being pulled because of a longer tail to the right, which makes that a right skew distribution. If x bar is less than x tilde, then it works just the opposite. And you can see it here if you have a left skewed distribution. Of course, the mean is going to be pulled to the left. The mean is always pulled in the direction of extreme values or the direction of a longer tail. So if the mean is less than the median, that must mean that your distribution is left skewed. Of course, if they're equal, then you have a symmetric distribution. The nice thing about symmetry is the center is obvious in a symmetric distribution. Pretty much any measure of center will be at that point of symmetry. So the mean and median will be the same. They'll be right at that point of symmetry. Now, of course, you always have the other issue of, well, when are the points close enough to say it's symmetric? Because in reality, when you collect data, they're never going to be exactly the same. So if your mean and median are equal, of course it's symmetric. If they're close together, we still say we usually throw in the term fairly symmetric, and we'll say it's a fairly symmetric distribution if the mean and median are close together. If they start getting far apart, then we'll start saying that it's skewed. But it's kind of a judgment call as to when they're far enough apart to be able to say it's skewed, and when they're close enough together to be able to say it's symmetric. A lot of that just comes really with experience. The more you do this, the more you get a good feel for when to say something is symmetric and when to say it's skewed. At the end of the day, with skewness and with extremes, at the end of the day, what really matters is how that's going to affect your statistic. If it's going to throw off your statistic, then you need to deal with the fact that you have a skewed distribution, or you need to deal with the fact that you have an extreme value. Extreme values sometimes are easy to deal with. You can just throw them out. In some cases, that is your best option. Dealing with skewness is not always easy. We love to see symmetric distributions. We can still analyze skewed data, but you got to think, even something as simple as a mean and median, or the center of the distribution. The center of the distribution is easy in a symmetric distribution. The center of the distribution is not so easy when it's right skewed or left skewed. You look at the mean and median and they give you different values of center. So all those things are easier in a symmetric distribution. We like to deal with symmetric data. Of course, we have to deal with whatever data we collect. So those are the main things in this section. The main things are the graphs. And then just make sure you understand that summation notation. And then we're starting to introduce these numerical summaries of data. We've started with this idea of measures of center. That is it for section 2.